Welcome in, and thanks for joining us for today's deep dive. I want you to just consider your own home network for a moment.
Oh, yeah. The source of so much pain.
Right. We all rely on Wi-Fi to run our lives, and, we all inevitably hit that wall of frustration when a connection drops or...
Or your bandwidth just mysteriously throttles right during a critical task.
Exactly, like right in the middle of a meeting. And the standard consumer reflex there is to just, well, throw money at the problem.
Yeah, you just assume your hardware is obsolete.
Right. You go out, you buy whatever shiny new router boasts the highest theoretical throughput on the box,
Yeah.
and you swap it out, hoping the network topology just magically resolves itself.
But very few of us actually apply a strict scientific methodology to evaluate the existing network state before introducing new variables.
Which is wild when you think about it.
It is. And that consumer reflex is exactly why home networking remains a black box for so many people. We treat routing hardware like a toaster, like an appliance, rather than a dynamic computational node.
Yeah, just plug it in and hope for the best.
Right. But today's source material, it approaches this from the completely opposite end of the spectrum. We are looking at a process of meticulous, deliberate environmental evaluation.
Absolutely. So we are pulling from a fascinating blog post published in February 2026 on kianmeng.org. The author, Eng, refers to himself as an old software plumber.
I love that phrase.
Me too. And the post is titled Notes on Networking Partnering, Benchmarking Wi-Fi 4 Before the Wi-Fi 7 Upgrade.
Which is quite the jump.
It really is. And our mission for you on this deep dive is twofold. First, we're going to dissect the actual diagnostic methodology of isolating network bottlenecks. But we are also mapping out the underlying psychological framework of a lifelong tinkerer, someone who documents their digital and physical environments with just absolute granular precision.
Yeah, to contextualize the benchmarking here, we really should establish the generational leap Eng is preparing for.
Let's do it.
So he is moving from an aging Wi-Fi 4 deployment.
That's the 802.11n standard, right?
Yeah, exactly. And that is locked to the heavily congested 2.4 gigahertz band. And he's going directly to Wi-Fi 7, or 802.11 BB.
Skipping a few generations in between.
Just a few. That is a massive architectural jump. I mean, Wi-Fi 7 introduces multi-link operation, 320 megahertz channel widths, and 4K QAM.
Yeah.
It spans the 2.45 and 6 gigahertz bands simultaneously.
It's a completely different beast.
It is. But Eng refuses to simply plug in the new 802.11 BB access point. He requires a quantitative baseline of his 802.11 in an environment to actually accurately measure the delta in performance.
Okay, let's unpack this, because the way he establishes that baseline highlights a really common diagnostic trap.
Oh, the bottleneck.
Yeah. So Eng's legacy router is running OpenWrite.
Which is great.
It gives him root access and the ability to run command line utilities directly on the hardware itself.
Right.
So he opts to use iPerf3, which is a standard network throughput testing tool. He spins up iPerf3 in server mode directly on the OpenWrite router and then runs the client side on his personal PC.
Pushing a synthetic payload across the wireless bridge.
Yeah.
Exactly. Which sounds fine, right?
It seems like the most direct way to measure the link state. I mean, you want to test the connection between the router and the PC, so you make those the two endpoints of the test.
But the data he gets back immediately flags an anomaly.
Yeah.
The test itself introduces a localized bottleneck. Eng realizes that running the iPerf3 server daemon directly on the OpenWrite router is actually taxing the router's internal system on a chip.
Which a lot of people wouldn't even think about.
Right. Generating those synthetic packets in user space and passing them through the kernel's network stack requires CPU cycles.
And on older hardware, that's expensive.
Super expensive. The processor on that older Wi-Fi 4 router is hitting 100% utilization just trying to build the payload, meaning the CPU is bottlenecking the throughput long before the actual 2.4 gigahertz radio hardware breaks a sweat.
It is the equivalent of trying to measure the top speed of a high-performance vehicle using a stopwatch that freezes every 3 seconds.
That is a perfect analogy. If your diagnostic tooling introduces its own hardware limitations into the telemetry, your baseline data is contaminated. You cannot determine if the slow throughput is due to RF interference, driver inefficiency, or just a CPU interrupt storm on the router itself.
Exactly. And Eng recognizes this right away and immediately restructures the test topology.
He takes the router out of the equation.
He does. To bypass the router's CPU bottleneck, he completely removes it from the compute path. He spins up a secondary peer machine on the same local area network and shifts the iPerf3 server daemon over to that.
Smart.
So now, the iPerf3 client on his PC pushes the payload over the Wi-Fi connection through the OpenArt router and down to the peer machine via a wired LAN connection.
Which means the router is no longer generating packets.
Right. It is just executing its core function, routing them.
And by offloading that compute overhead to a dedicated peer machine, Aang isolates the wireless bridge as the primary variable. The router SysC is free to dedicate its resources strictly to managing the wireless frames and the routing table, which gives him a much clearer picture of the actual airtime efficiency.
But, and this is the kicker, with the test architecture corrected, he runs the benchmark again. And the throughput is still remarkably low. Even with the CPU limitation resolved, he's seeing speeds that hover around 20 to 30 megabits per second. Now, we know theoretical maximums on 802.11n can hit 150 millibs on a single spatial stream.
In a vacuum, maybe?
Right. But Aang fully expected these degraded real-world numbers because of the physical realities of the 2.4 gigahertz band.
Yeah, the 2.4 gigahertz frequency is a notoriously hostile RF environment. Because the air is a shared medium, devices rely on CSM-MASI, carriers sense multiple access with collision avoidance.
Right.
Essentially, every radio has to listen to the channel, wait for it to be clear, and then transmit.
It's polite, but it's slow.
It's very slow. When you factor in the density of modern environments, dozens of neighboring routers, Bluetooth peripherals, IoT devices, microwave ovens, the noise floor is incredibly high.
It's just a wall of noise.
The amount of time your device spends just waiting for an open transmission window drastically pulls down your aggregate throughput.
And beyond the crowded airspace, Aang isolates another critical variable in his hardware chain, the client-side network interface controller.
Okay.
He specifically notes the use of a, quote, tiny nano adapter.
Oh, those little USB nubs.
Yes. And when you are dealing with ultra-compact USB Wi-Fi adapters, you are often relying on heavily compromised silicon. And more importantly, notoriously unoptimized Linux drivers.
Definitely. Poor driver implementation can lead to terrible buffer management or excessive CPU interrupts on the client side. That just compounds the latency introduced by the congested airspace.
Exactly. The combination of an overcrowded 2.4 gigahertz spectrum and an inefficient hardware driver creates an incredibly fragile link state.
And this fragility becomes explicitly quantified when we look deeper into the iPerf3 logs Aang documented.
Here's where it gets really interesting. Because the raw throughput speed wasn't the most alarming metric in the terminal output, it was the error correction data.
The retransmissions.
Yes. In one of the test runs, the system reported 21 retransmissions to successfully move a mere 5.29 megabytes of data across the network.
What's fascinating here is the cascading effect those retransmissions have on the transport layer.
Walk us through that.
Sure. When a packet is lost due to RF interference or a buffer overrun on that tiny nano adapter, the MAC layer has to negotiate a retry. If that fails, the TCP protocol kicks in.
Right.
TCP interprets dropped packets as network congestion. So not only does the sender have to retransmit the missing data, but the TCP congestion control algorithm actively halves the transmission window.
Ouch.
Yeah, it intentionally slows down the data rate to prevent further packet loss.
Which perfectly explains the real-world symptoms you experience when your network degrades. 21 retransmissions for 5 megabytes of data is a massive overhead.
Huge overhead.
If you are trying to stream a 4K video or hold a live remote meeting, that invisible packet loss is devastating. UDP traffic, which powers most video calls, doesn't even bother with retransmissions. It just drops the frames entirely.
Which is exactly why your video stutters and artifacts.
Right. And TCP traffic, like loading a heavy web application, will meticulously resend those packets, which is why your browser hangs for 10 seconds, despite your operating system displaying full Wi-Fi signal bars.
Signal strength indicators are largely cosmetic.
We really are.
They tell you the amplitude of the carrier wave, but they tell you absolutely nothing about the signal-to-noise ratio or the packet error rate.
Right.
Aang's benchmarking cuts through the cosmetic UI and quantifies the invisible chaos of the RF environment. By isolating the variables distance, driver overhead, and local compute bottlenecks, he secures a mathematically rigorous baseline.
So when he finally provisions that Wi-Fi 7 hardware, he will know exactly how many milliseconds of latency and how much throughput he has reclaimed.
Exactly.
Now, the networking benchmark alone is a fantastic case study in hardware diagnostics. But we have to zoom out and examine the broader context of this documentation.
Because it's not just this one post.
Not at all. If you navigate to the sidebar of Aang's blog, the sheer volume of data he has archived is staggering. He has been actively publishing these technical logs since July 2011.
Wow.
And the velocity of his output is accelerating. Looking at his yearly archives, he published 730 posts in 2022.
That's 2 a day.
He had 730 again in 2023, 732 in 2024, and 730 in 2025.
That is incredible consistency.
That is consistently 2 deeply technical or highly detailed reflective entries every single day, uninterrupted for years.
Maintaining that level of disciplined output requires a fundamental integration of documentation into one's daily cognitive process. It ceases to be a blogging hobby and becomes a functioning second brain, an externalized ledger of every hypothesis, test, and conclusion he generates.
And the breadth of his focus is what makes this archive so compelling. We just walked through notes on networking part 9. But looking at the index for February 2026 alone, he is context switching across completely disparate disciplines.
What else is he working on?
Well, he maintains a series called Notes on Haskell Programming. That one is up to part 70, where he's debugging parallel execution.
Okay, very technical.
Right. But then he has notes on fish keeping at part 202, analyzing beta spawning behaviors.
Oh, wow.
And then there is notes on gardening, currently sitting at part 821, where he is diagnosing root knot nematodes, propagating Brazilian spinach, and evaluating why a specific mint plant is failing to thrive.
If we connect this to the bigger picture, this repository represents the purest distillation of the hacker ethos. And I use hacker in the traditional MIT model railroad club sense. An individual who looks at a complex system, dissects its components to understand the underlying mechanics, modifies the variables, and meticulously records the outcome.
Yeah, it doesn't matter what the system is.
Exactly. Ang treats an Elixir library, a Linux kernel, and the nitrogen cycle of a fish tank as equivalent systems to be optimized.
He applies the exact same diagnostic rigor to organic chemistry that he applies to an 802.1n1 Wi-Fi protocol. When he's figuring out why his red pineapple plant isn't blooming, he is isolating variables.
Soil pH, ambient light, phosphorus levels.
Yes, with the same systematic precision he used to isolate the CPU bottleneck on his OpenBret router. It is a unified theory of troubleshooting applied to both binary and biological ecosystems.
This approach is deeply intertwined with his advocacy for open systems, too. Ang explicitly notes his dedication to flaw-loss-free Libre and open-source software.
Yeah.
And he actively directs his readers to support organizations like the Electronic Frontier Foundation, the Free Software Foundation, the Tor Project, and Wikipedia.
He's living those values.
He really is. His entire blog is an exercise in open-sourcing his own intellectual process. By publishing his failures, his terminal outputs, and his botanical experiments, he is contributing to a decentralized, democratized web.
So what does this all mean? We started by examining the underlying mechanics of why a 2.4 gigahertz Wi-Fi connection drops packets, and we've ended up uncovering a comprehensive framework for interacting with the world.
It's quite the journey.
It is. And for you, the core takeaways from Ang's methodology are highly applicable, regardless of your technical background. First, never assume the integrity of a system without establishing a quantitative baseline.
Right.
Second, relentlessly audit your diagnostic tools to ensure they aren't introducing their own bottlenecks. And third, document your processes.
Because an undocumented failure is just a frustrating mistake.
But a meticulously documented failure becomes actionable data.
This raises an important question for you to consider long after we wrap up today. We have examined how Ang applies highly structured, deterministic frameworks like isolating CPU utilization or mapping TCP retransmissions to deeply chaotic organic environments like algae blooms and root systems.
Yeah.
What happens when you actively cross-pollinate those disciplines in your own life? Consider the possibilities if you approach an organic, interpersonal problem with the dispassionate, variable isolating logic of a network engineer.
That's a fascinating angle.
Conversely, what breakthroughs might you achieve if you treated a rigid, sterile, technical architecture like a living, breathing ecosystem that requires a delicate environmental balance to thrive?
Applying network topology logic to a garden and botanical patience to a server rack. It is a phenomenal mental model to adopt. Thank you for joining us for today's deep dive. Keep isolating your variables, keep logging your data, and keep questioning the mechanics of the invisible systems running your world. We'll catch you next time.